So I recall what was our final discussion yesterday. I said that log geometry allows, among other things, I don't say that its aim is to do this. It allows many things, but for us here, what will be important is that it allows to construct the cut of a complex variety along a hypersurface in an intrinsic way. And now, under supplementary conditions, one gets topologically the same as removing a tubular neighborhood of the hypersurface. So this is what you have to have in mind as a moral of what I will show now. And I told you that the baby example, which some people could reject, they say, no, we couldn't understand anything on a baby example. My philosophy is the opposite, is in order to be able to give meaning to a general definition, one has to have in the hands very simple examples to enrich our usual intuition. So the baby example is that of the origin in C. So C is a complex line, so it's a complex variety. And here we have a hypersurface in it from the viewpoint of complex geometry. And here in C we have a preferred coordinate, Z. And I said simply yesterday that the classical passage to polar coordinate, Z is equal to R EI theta, this can be seen as a map from the space of the variables R and theta. R varies, in fact, between 0 and plus infinity. Theta here varies in the circle R over 2 pi z. So this is a circle. I draw below the topological space. So we have this Cartesian product, and therefore this Cartesian product is in fact an annulus. So it is as if we have replaced the point O by this circle. So this circle is this one here. And here, this half line is this one. And now you see that here the map goes to C. And if we take not only the real non-negative half line, but also several other ones, as this one, and say these ones, you see that here they get separated. And this is a crucial aspect here. And now let's see, because we go towards logarithmic geometry, I will show you first what this has to do with the logarithm. So imagine that you want to define log of z. So log of z is defined outside the origin on C star. And you can really define it in which way? Well, you take the logarithm of this, and it is log of r plus what you find here in the exponent, I theta. And because we said that theta belongs to this, it means that this logarithm belongs exactly, in fact, not to the Cartesian product here, but to 0. So here you took the logarithm of this, so to the half line minus infinity plus infinity plus I times this circle. So you see the logarithm is well defined. Seen in this way, it is not multi-valued if we decided to put the imaginary part in a circle. But the problem is that it does not extend by continuity to the origin. Problem, this map log from C star to this object here does not extend by continuity to the origin of C. And that is what is solved by this operation of passage to polar coordinates. Which is also called under the name of real oriented blowup.
But did you really want to include minus infinity for the log or not?
Yes, because I want to extend to the origin. So if I want to extend to the origin, I look what happens when I tend to the origin. So when I tend to the origin, precisely r goes to 0. And so if I want to give a value at the limit, I am obliged to put minus infinity there in order to be able to put the extension. So you see, I can extend by continuity if I look only at the real part. But I have a problem with the imaginary part. And these half lines which I drew only 4 of them, are exactly the level sets of theta. And here the problem is that they met all of them here, which says that depending on the direction through which I converge to the origin, I should be invited to take another limit. And I cannot do it. That's why I cannot extend by continuity. And this map will allow this because here I separated the level sets of theta. So this is a sign. If you cannot extend something by continuity, in general it means that if you look at the levels, they will have a base point. Then separate things going there. This is a kind of blow-up process. And if you separated them, now the level sets won't meet anymore. And this is a geometrical sign of the fact that you can define a function. And this is exactly what happens here. And now you see that on this, I will write it carefully on the other blackboard. Yeah, this is okay. But if we lift log to the real oriented blow-up, here I put as an index the name of the variable I use there. Then I may extend by continuity to the boundary which replaces 0 in C. So I could not to 0. I replace 0 by the boundary, which is a circle, and now I can because you see the formula of the logarithm there. In terms of r and theta is simply log r plus I theta. And that it's completely well defined on the new thing. So here the map is simply r theta goes to log r plus I theta. And so what is the target is exactly the same as before. So from the Cartesian product of these two objects to their sum multiplied, the second one being multiplied by r. So you see that this geometrical object there on the right is the one which allows to define the logarithm everywhere. This is a way to understand the log of log geometry. Yes? Oh, sorry, yes. The second, yeah. I always make this confusion. Thank you. Of course, minus infinity. Okay? So you see, very easy. And now we said that we would like to arrive at something valid on any manifold. You know that on any manifold, in order to get something intrinsic, one has to get rid of the choice of local coordinate. So let's try to reformulate this without using specifically z. Let's get rid now of the variable z. For this, we say, what's the usual way of getting rid of it is to say we look at the complex line as a complex curve, which means that we look at all possible functions defined there. That's the structure sheet of holomorphic functions. Z is only one of them. And now look, take a function. I'm working just near the origin, so I look at the germ of a holomorphic function on C, with C, holomorphic. And now I ask, can I define log z, log f? Well, let's still make a relation with this preferred variable. If you use it, you know that f of z, now it can be seen as an expression in z, may be written as a unit, something which does not vanish at the origin. Z to the power n. In order to do this, we need to assume that f is not identically 0. So I assume here that it is not the 0 function. And here I assume that u of 0 is different from 0, which tells that indeed it is a unit. So now you see that if you want to define log of f, well, by the fundamental property of logarithm, this should be log of u. No problem for defining this because u does not vanish at the origin, plus n times log z. Okay? And you see that once you know what is log z, there is no problem. All these logarithms are defined. But now you know that in order to be able to define the value of log z, you have to go above there. And there, the value of the logarithm at the origin is not unique. You have, in fact, many points which give a value of it. So let's look. Each choice of point P in this circle here. So I will put a color so that you see where P varies. P varies here only on this circle. Gives a determination of log of f for any function f which belongs to the local ring of C at 0 without 0. And then let's look at this point P through its action on f. So you see here we make the Dedekindian mathematics. Here we try to define new points. We say we would like to understand intrinsically what should be this new point from the viewpoint of what we already have, which is the initial curve. This is what had done Dedekind for the construction of real numbers. He said, well, I have in my hands only the rational one. I have the intuition of a real number. What's my intuition? Is that it lies somewhere between the rationals. So, what does it do to the rational? It cuts them. Again, we speak about cut. So a real number is exactly a cut. So we will do the same. This new point does something to what is already existing, which are these holomorphic functions. And we will see what it does to them. So for this, we look and we see that we can evaluate the logarithm. But if you evaluate the logarithm, I just told you that the problem was this I theta. It's the same as the exponential of I theta. So giving a meaning to I theta is the same as giving a meaning to the exponential of I theta. And exponential of I theta is z over the modulus of z. Or in this generality, you want to give a meaning to f over the absolute value of z. And this z over z, here it belongs to another circle, S1, which is a unit circle in C. In fact, it is a subgroup, multiplicative subgroup of C star, seen with multiplication. And I insist on this when I tell you here you have C star with multiplication, because this is a crucial baby object which allows to build all toric geometry. And you begin to see here relation with toric geometry. So in fact, you cannot see here anything, but I tell you. Here what appears is this multiplicative group. Okay, so this is to say only that I won't write any more I theta. I will focus only on z over the absolute value of z, or f on absolute value of f. And now look, what does this p do? It sends f to f over the absolute value of f. You have no problem for this if f does not vanish at 0. Because there, you can do on the neighborhood, you take something divided by something non-zero. And the problem is what happens if f vanishes at 0. And you see here by this computation that it is enough to give a meaning to z over the absolute value of z. And precisely on this space, it has a meaning. So P is a way to give a meaning to this. So let's see what it does here. It sends, in fact, O C0 minus 0 towards S1. And now if you look, S1, I said that you look at it multiplicatively. This also you look at it multiplicatively. And we see that as a map like this, it is a morphism of monoids. Why monoids? Here on the right you have a group. But here on the left you do not have a group, because the inverse of a function here is not holomorphic if the function vanishes at 0. You don't only have multiplication. So that's the moment when you see here for the first time the need to look at objects which are monoid. And they are really the algebraic building blocks of log geometry. Yes?
Very simple question. You must evaluate at a point, maybe? You do f over f. This is a function. So
it
you
is
want
the
to
evaluation at P. So what I say, in order to give a meaning of this, you take f over modulus of f, but you evaluate above.
Okay.
So it means that you lift it outside 0, then you look at the limit at that point. There.
But this means that above is defined.
Above, what I said is that you can make the extension by continuity and you evaluate it at that point. But this is because we have done our drawing. And now we want to say, well, I want intrinsically, in terms of only the complex analytic structure, without giving a privilege to the variable z, construct those points of that circle intrinsically. And what I say is that they appear as morphisms of monoids. And here, in this way of looking at them, you see that z disappeared. It plays no role. So this was simply everything, the process to get rid of the choice of a variable, which is fundamental each time one wants to get a globalization of things which initially were written in local coordinates. Okay? So now you will see that from here we will be able to define this in that general context by imitating what happens here. So I keep this objective here. And now I give names here. We have a complex variety, and inside it I will put a hypersurface. And I want to cut x along h. So we will do the same as here. We imitate what we just did for C, and inside C, the origin. This is a baby example of a hypersurface inside in a complex variety. A priori, no. You do not have to. Not a hypersurface. You will see that when we think it, you have to imagine anything. What I say is that in this generality, what we will get does not have the topology of removal of a tubular neighborhood. I will say afterwards when you are sure of that. But you will see that in this generality, you get nevertheless a definition. And that definition will lead you at the same time at the notion of log space and at that of generalized real-oriented blow-up. And then I will give you the attribution. But what I want to do is to I will show you just now when I put the big complete definition. So what we do, first the new space will be defined as a set. So I describe its points. So there are points, the points are pairs, a point of x. Because you saw here the new space, I removed the drawing. So let me put it again here as a reference. This is x. Now this is a. Okay, and this new space will be called here x, say, comma h log. In the literature of log geometry, this will be an example of, this is called under various names. It was an operation which was introduced by Kato and Nakayama in 1999. So some people call it Kato-Nakayama space. August proposed a name which I like very much, and I will use it now, the rounding. Because you see, you created a circle where it did not exist, and you will see that it creates a lot of circles and tori. So things become rounder. And I think this is very good to have in mind, that by this operation, you make things rounder than before. And also, he created the name Betty realization. So I think that this rounding really points to something which happens morphologically, and that's why I prefer it among the others. But you have to know that when you look in the literature, you have to type all three names to find what happens about this. So, I hope to have explained you why to put an index log for notation of this new space is good. I showed you why it allows to define the logarithm. And now, let me come back here. Its points project to a point of x. So you can say first, to determine a point here, we just say first which point on x we choose. So this is the first thing to be done. And now we have to specify a second object, P. And what is P? So let me say first that x belongs to x. And now, what is P? It's a morphism of monoids, so I write that it belongs to Hom in the category of monoid. From what? And here is a crucial thing. There it was a little difficult to see what's the correct definition. Here, what is important is that our function, which is not identically zero, then it may vanish at the origin, but it surely won't vanish outside it in a sufficiently small neighborhood. And this is the definition which is taken here. So what we will take here as the analog of the multiplicative monoid on the left is that we look at functions which cannot vanish outside H, but they are allowed to vanish on H. If you take the usual sheaf, you look at a hypersurface, in usual algebraic geometry, what one takes is OX of H of minus H, which is the sheaf of ideals of functions which have to vanish on H. But they may vanish also outside H. Those vanish at least on H. Here is nearly, they can vanish on H, but at most on H. It means that they cannot vanish outside. So it means that outside they are units. That's why this is not a standard notation, it's the one we use, and I think when you understand this, it's very useful for thinking. We use the same notation, but we put star here. So you remember that you allow to vanish on H, but in a slightly different way. You won't oblige, you say, it does not have to vanish at least on H, it has to vanish at most on H. And you look at this sheaf, and you take its stock at the point X. So this is a sheaf on X, and you take the stock at small x. This is a multiplicative monoid. Monoid of germs at X of holomorphic functions on X, big X, which vanish at most, and not at least, at most, on H. So then by pure logic, you see that it is a multiplicative monoid. And the target is the same as here. So you see, it's absolutely intrinsic. And the crucial object was this one. And in fact, we did not finish, because now we say, I said that Ox star, the functions which do not vanish, well, we have to impose that for them, this morphism gives f's over absolute value of f, such that p applied to f is equal to f over the absolute value of f, and this for any f belonging to Ox star at small x. And this is set theoretically this new space. I said at the end that we impose, here we have the functions which do not vanish. For them we have no difficulty in saying that we have to take the sign of the function, f over absolute value of f. And the problem was, what happens if the function vanishes? And we say, well, a point which we have to add there is a way to give a meaning to this. And in this way, you see that this is a space xh log. So this is. And it comes with a map obvious to x, which is called t xh. Tau, sorry. And this is a rounding map, where simply the pair xp is sent to the point x. This is a big generalization. So first remark is that in the case when D in X is a normal Rossing divisor, in a smooth complex manifold, complex variety, so complex manifold, this X D log is simply the real oriented blowup of X along D. As far as I know, the first person to use it in singularity theory, already used in singularity theory, by Acampo in his 1975 or 1976 paper on the zeta function of monodromy. And there he defined it differently, and a definition which is also useful for getting intuition. I won't give it to you because I want now to explain why this one is powerful. Question?
Yeah. A question just for clearing my mind. Ox star is the units, right? Units at, so that's the functions which do not vanish at 0, right?
Yes. At the point small x.
At the point small x, yeah. So, but the point P is above the origin.
We want to build points above small x. Here we are not on the origin. It's abstractly you fix the point of big X, and you want to put new points above it. And the new points are all the ways to extend the sign of f to functions which vanish there. So it's exactly what we treated over C.
Okay. So when you write Pf equals f over modulo of f, this is at x. This is estimated at x.
Yes.
Okay. Okay.
So, yes, indeed, that I did not write, and
Okay.
this I should
Thanks.
put here
Okay.
of at x. Yes, thank you. Yeah. Yeah, it's very important there to have all the symbols carefully written. So you see also there is a kind of philosophical question. If you think how many of you were taught when they were students how to build definitions? In fact, it's very strange. It seems that all over the world, we tell definitions to students. They said, God told them to Moise, you have to learn them. You don't know the definition, 0. But you see there's a struggle to find good definitions. And in fact, I think it would be also for us extremely interesting to see how to teach some classes where the aim is at the end to arrive at a good definition from several examples. I don't say I know how to do it, but in any case, what I try here is to make you to feel a flow which leads to this object. And I always spend a lot of time to try to mentally imagine natural flows which lead to definitions, because I am completely unable to remember definitions logically. So I don't know how you are, but in any case, for me, this is a fundamental process, and it takes a lot of time and energy. So this is what I tried to communicate. And now let me try to extract something from this definition. You see here that appeared a new kind of object. This is a logarithmic structure. So let me extract now this object, what we used for this. In the previous definition, the crucial object was the sheaf of monoids OX star of minus H. And monoids, and I put here the multiplication. And it's a sheaf on X. And now there is something very important. When you say it's a sheaf of monoids, it means that simply you think about the sets of sections above an open set as monoids, nothing more. So you forget that they are functions. You pick an element there in a sheaf of monoids, you cannot evaluate it anywhere. If you want to evaluate such an element at a point, you have to remember that it is a function. So it means that this sheaf of monoids has to come with a way to remember. And this way is to tell for each element here to which function it goes. So this comes with an arrow here towards the structure sheaf, OX. And this is also to be seen as a sheaf of monoids. So the structure sheaf is not to be seen here as a sheaf of rings, but as a sheaf of monoids. And this has to be an arrow there. And now, this is nearly the definition of logarithmic structure. Let's extract it. Definition. And pay attention, here there are no complex numbers. No, and I will tell you here, now you see you don't have C. So now I say, let XOX be a ringed space. And if I want it, but I don't want to look very clever, I say orthopos, but I won't write orthopos. So, but in any case, this is something valid over any kind of space you need. And you have a ring space. So, a pre-logarithmic structure on this space, and now I say this space has to be thought as a ring space. The sheaf of rings here is not to be taken over a ring space. On X is the following object, mx with a multiplication. This is a map alpha x. Here I have OX with multiplication, where this is a sheaf of monoids. And this is an arrow in the category of morphisms of sheaves of monoids. So, mon over X, the category of sheaves of monoids. What is a log structure? In fact, this is a log structure. Let's see something more, a property which we can then build here as a general property. You see that here, by definition, we took all the functions which vanish at most on H. But among them, you have all the functions which do not vanish at all. So it means that you have all the units here. So let's take here the Prelog structure. Alpha x is called a log or a logarithmic structure in the sense of Fontaine-Illuzy. And some people add Cato because he wrote the first text, the first evangel, which gave to the rest of the world the good news of the existence of this object. When is it a log structure? When, let me write again this map. So a log structure, if now look here at the units, the functions which vanish nowhere. These form a group. This is general. Each time you have a monoid, you have here the maximal group inside, which is a group of its units. And now you can take the pullback here. So you have automatically here the alpha x minus 1 of OX star. This, in fact, is here. And what one asks is this to be equal to the units of this sheaf of monoids. So I will give you again the baby example such that you feel what this condition means. And you will see that indeed, this last condition is the one which says that you got rid of choices of local coordinates. This means that we got completely of the choice of local coordinates. And in order to see this, let's make the baby example. But now the definition is complete. Let me see if I did not forget something, a word or something else here. So the if is this condition. Prelog is this. Is called a log structure if we have this equality. So this means that you can look at this sheaf of monoid as an extension of the units here by something else. But this something else adds no unit. You had the units from this. And let's look on C. So an example of Prelog structure. We start from C, and again we look at the origin inside it. So the drawing is this one. And we said that we chose a local coordinate, Z. But then you can see that Z is, I choose 1 and I send it to Z. Okay? And now 1 can be seen as an element here of the additive monoid N. And I send it, in fact, here, what? To O. What I said is OC star of minus the origin. So here O has to be seen as a letter labeling the origin and not the number 0. This is the origin. So what is N? You can look at it as the constant sheaf of monoids, N, over the whole space C. So it's exactly something like this. This is a map alpha over C. Okay? But you see that if you look at the units here, and you take the pre-image, you do not find inside N all the holomorphic functions which are units. This is extremely small. So we want to add them, which means simply that we will allow to multiply Z here by all those functions, by all functions which are allowed to vanish at most at 0. So in particular, we may multiply by itself. So we get the powers of Z, Zn. And we can multiply also by units, U. And we get U of Z times Zn. And you saw that in this way, we get exactly all the holomorphic functions in that sheaf. So the last step there is a step where you add all the units, if you don't have them, to get a logarithmic structure. And by an abstract nonsense, there is a property which tells that every time you have a pre-log structure, there is an associated log structure. And you have to think about that as the step when you get rid of choices of coordinates. Exactly like in classical manifold theory, you have to learn to compute in coordinates. In fact, you cannot do anything about manifolds if you don't know how to compute in coordinates. But you have also to be able to have a global viewpoint of how those things get intrinsic meaning. And that's why, for instance, partial derivatives became vector fields. And we see them as the velocity of water. And we look at water, and that's very useful mentally. But it's, again, a transform of this kind. Yes?
There's something I'm not sure whether I get properly. So this definition up there, you say the pre-image alpha x to the minus 1 of the units should be the units in the monoids.
Yes.
Thing. But here the monoid is n and the units is just 1.
And this is what I say, this pre-log structure is not a log structure.
Well, but the pre-image is just 1.
No, the units here are all the non-zero functions.
Yeah, but if you take...
I look at the units in the target,
yeah,
and I take their pre-images. So the units here, multiplicative is just 1, but here it's much bigger. Here it's the sheaf of all invertibles.
Isomorphism. You want isomorphism on the bottom arrow, maybe.
Oh, sorry. Yes, of course. Yeah. Yes, of course. Yes, sorry. Something else is wrong? Yes.
So here in the definition, even in the Prelog structure alpha x, the target is O of x, OX, yes?
Yes.
And is that the same also there?
Sorry, no, this
So
it's an error. I do not need to put it.
Left-hand side.
No, I do not need to put it here. No, because it precisely here Z will generate it by the fact that I prescribed one function which vanishes there. So no, you are all right. I told you that I never understand things from the symbols. I always am, but it's very good to look carefully at the symbols here. So this is a sheaf of non-zero holomorphic functions. Sorry. Yeah. But that's good. It means that you really understand what happens here, and this is great. Yeah. So it's written in this way. Indeed, it's a logarithmic structure, a Prelog structure. This is a Prelog structure, which is not logarithmic. But you have to know that this is a way to prescribe such maps from finite type monoids is the logarithmic notion of chart. And in fact, in the log category, this is called a chart. And there is a notion of coherent log structures. They are exactly those which can be covered by charts in this sense. So I won't develop that language, but you have to know that indeed prescribing something like this is the analog of the choice of here is a variable Z. And as I told you, each time you have a pre-log structure, there is canonically an associated log structure. And now the power of this is that one has a category. There is a category of log spaces. And as a homework, if you take that definition, I let you define what is an arrow in that category. But in order to see geometrically the context, we want to apply example. If we are in a case, if x and y are not log spaces, but complex spaces, each one comes with each hypersurface. Then, as before, one can define associated log spaces, which are called divisorial log spaces. On the first one puts this sheaf of monoids with the usual inclusion. And the same for y. Okay. And now, a map of complex spaces from x to y, f, induces a log map from this to the analog for y by pullback of function. This means that the pre-image of the hypersurface in the target by f is included in the hypersurface in the source. So you see that in particular, if you have the situation which leads to Milnor fibers, if you are on a space, say y, or you resolve singularities, you arrive at a y tilde, and here you have a function which goes to C, and you are interested on the special fiber which is above the origin in C, and here you have the fiber here, you see that the preimage of 0 is x. So you have equality there. So it means that if you endow C with a divisorial log structure given by the origin and the divisorial log structure given by x on y, then you get a logarithmic enhancement of your map. And you can begin to think about it in the log category. And in particular, you can do that rounding on both sides. So what the principle here is to apply rounding to this situation on a resolution of singularities. And I will finish with this. And I'm very sorry I wasn't able to tell you about the tropical aspects. I'm very sorry. But the title of the lectures were about log geometry, so I want to make you understand this fact. If now we started from our map here, F goes to C, we are interested in this special fiber above the 0. And we make here some modification which resolves in some sense this. And here we are interested in the pre-image of F. So let's say that this is F tilde here. This will be here F tilde minus 1 of 0. Because we take the total pre-image of 0, we can take the associated logarithmic structure. A symbol which is used in the literature is when we do this enhancement is to put a dagger here. So we are looking at this map. And it means that here we put the log structure defined by O, and here we put the log structure defined by this. And now the great thing about log structures is that they can be pulled back. In particular, they can be restricted. So I restrict it to the special fiber here. And I restrict it to 0. And now I concentrate on this. And I look at this. And this, I will round it. And when you round this, simply you put log. So you see here the fact that there is a powerful formalism is that you can add things like this. And if you do not have the baby examples, you don't understand at all what happens. But this is a theorem, a particular case of a theorem of Nakayama and August from 2010, is that if the map F tilde is toroidal, and we need in fact a little more, but let's say the easiest example is this is toroidal, then in fact this last map, this will be F tilde log is a locally trivial fibration and say is a model of the Milnor fibration over the circle. We need to have also the monodromy. And the great advantage of this is that because we had that canonical construction, this space projects by the rounding map, it projects to this special fiber. This is a map of rounding. And because this object is decomposed into components, this cuts canonically this map into pieces. And this is the reason why it helps proving the Neumann-Wahl conjecture. But we have to apply it carefully to a carefully chosen modification dictated by the equations. And that is a part where tropical geometry enters. Thank you very much for your attention.